Hey folks, I want to go through system design for Uber today, and uh, that's this video is going to be about. So let's get started on this one. So this is system design for Uber. So before the first thing we need to do while coming up with system design for any system is to figure out what are the core requirements for that system. This will be true for both the functional and non-functional requirements. So let's start with the functional requirements first. The first requirement here would be that a rider should be able to enter the source and destination locations and then get the fare. So rider should be able to enter the source and destination locations and get an estimated fare. Now based on this estimated fare, the driver would want to book the service. So rider should be able to book a ride based on given fare. And the third functional requirement here is that the driver should be able to accept a given ride. So the driver should be able to accept a given ride. Now we have some non-functional requirements, sorry, some out of scope requirements as well, which would be not available, not possible to discuss in this particular video. So let's start with them. Let's just write them out as well. Out of scope. So the first thing here is that differentiate between different kind of cabs. Differentiate between different types of cabs. Go, auto, etc. Then the second would be schedule a ride in advance, and the third would be, let's say, rate a rider or a driver. Now moving on to some non-functional requirements. First is that we should have very low latency, which means that we should be able to book or find a driver in a given time frame, let's say 60 to 90 seconds. Now what else? One way to figure out the non-functional requirements is look into the CAP theorem. Do we want our system to be consistent, or do we want our system to be highly available? The caveat, the good thing here is that we need consistency and high availability in different areas. So we need strong consistency in situations where when we are booking a ride or matching a ride. So one driver should not be assigned to more than one rides at a time, or a driver. So yeah, that is the first one. So strong consistency, one ride per driver at a given point in time. That is one. And then we'll have high availability, which is the system should be up all the time. Yeah, high availability is, I mean, like this, should be up all the time. And the fourth would be handle surges. So you can think about situations where a lot of people start booking cabs at a given point in time. This could be, let's say, the final match of World Cup happened last year in Ahmedabad, and all the people who came out of that match would have wanted to book the rides at the same time. So we should be able to handle surges. Let's say 10,000 to 100k requests at a time. Just like functional requirements, we'll have some out of scope non-functional requirements as well. The first would be, let's say, CI/CD pipeline. The second would be that privacy. So we have something known as GDPR guidelines. We are not going to look into them. Third would be we are not going to work upon monitoring and logging systems. Okay, so now this is a good enough place to start. I will now move on to the core entities and APIs for the system. So let's go into core entities first. And there are primarily 4 entities here. One is rider, second is driver, third is the ride, and the fourth is your location. Each of these entities needs to be persisted in the database system for a system to be functional. After core entities, we have APIs. The first API would be a post API where a user should be able to, a rider should be able to request a ride. So this will be a /ride object, and this will, the input parameters would be source location and destination location. So what the rider is looking for right now in this request is what would be the estimate fare, and also what would be the area. So we will return here a partial ride object, and it's partial because the ride object doesn't contain all the information that could be there. For example, it doesn't contain the who the driver is. So yeah, that's why it's a partial object. The second request would be a patch request on the same resource, and this would be not exact, this will be a book. So now the rider has looked into the fare and the ETA, and they are happy with whatever they have been suggested. So now they want to book the ride. So this will this is the next endpoint, and here we have ride ID equals to ID. Yeah, and one thing to note here is that I am not adding the details of the user in the payload. This is basically a good practice for security purposes. That information would be available in your JWT tokens, the headers, user ID in headers. Let's say JWT tokens. The reason why we have this kind of system in your headers is that if we have the system in the payload request, then the user could be impersonated. So that's not a good practice. Using that kind of sensitive information headers, JWT tokens, is a better practice. So so now the rider has requested a ride, and the return type of this request would be null. We are not giving anything back to the user right now because it will take some time to find the rider. So it's just a asynchronous call, asynchronous request, I should say. Not HTTP wise, but I think you get the point. Now the next thing is a driver should be able to request, should be able to accept a ride. So this will be again a patch request on the same object, which is ride/accept, and the return type here would be location, the location of the user. So we have what do we have? We have ride ID equals to this. Now once the user has reached the location of, once the driver has reached the location of the rider, we need another endpoint which will let the system know that the ride has started, and the driver now wants to know where the drop-off is. So this will be a ride/update, and again, so this will either have a location object as return type or a null object. The null response type is in the cases when the driver has completed the ride and they just want to say that hey, the ride is completed. So there's no return type at that point in time. So we have 2 parameters here. One is ride ID, this one, and then we have also another parameter which is status, which could be, let's say, started or completed from a driver's end. The 5th API endpoint here would be location. So the driver needs to update the location where he or she is present as well. So this will be a post and slash location. Return type is again null. We do not need to give back anything specific to the driver. And here the parameters are location. Yeah, so that's it. So these are the 5 APIs which we need for these functional requirements to be functional, for the system to be functional. And with these two things out of the picture, we can get started with the high level design. So now let's move on to that. So for the high level design, let's start with Rider client. This will be a mobile device, iOS or Android, and the Rider client will make a request which will hit an AWS managed API gateway. AWS API gateway. So AWS API gateway is a one-stop solution for a lot of things. It does a lot of things for us, just 1 second. It does the routing, which API request should go to which particular service. Then the next thing here is load balancing. The next thing would be authentication, and it does a bunch of other services, other stuff as well. So now we have this API gateway, and the rider makes a request to the API gateway saying that post /write. Now this request now first of all goes to a booking service. So we'll have a booking service here, and the whole booking service, the whole idea of booking service is to create a booking and then estimate the fare and the ETA, estimate ETA and estimate fare for this particular trip. So we have estimate the fare and ETA for a trip, and there are multiple ways to do this. A system and a company like Uber will have sophisticated ML models to come up with this kind of a data, but for now in this particular design, let's outsource this to a third-party service. Let's say like Google Maps API. So we have a third-party API, and these two talk, and our booking service has the information now. With this information, our booking service will persist that data into a primary database. And let's talk about the different entities of primary database here as well. So first of all, we'll have a ride object which will have ID. It will have rider ID. It will have source, destination. It will have source location. It will have destination location. What else it will have? It will have something like, am I missing anything? Yeah, it will have an ETA. It will have estimated ETA. It will have estimated fare, and then apart from this, it will have a bunch of other metadata. So yeah, this is it good for now. And then we have a few other objects as well. For example, rider. These are important but not so interesting, so I will not spend a lot of time here. We'll have ID, we'll have government identification, we will have, let's say, one-to-many mapping to, we will not need to have that. So yeah, and then there'll be some other metadata as well. And similarly, we will have a driver object as well, which will have again an ID. We will have, cab number. We'll have registration number, and again we'll have, one thing we'll have here is a status. So whether the driver is available, or he or she is offline, or they are in a ride or stuff like that. So this will be available, status available, offline, booked, yeah, something like that. And then we will also have, we do not need location here, we'll come back to that in a while. So yeah, these are the objects which this particular primary database will have. And we can choose either of the databases, NoSQL or SQL. Prima facie, SQL looks like a better option here because the write throughput is not very high. If you look at the schema, the data fields, most of them, or a lot of them, are connected. There is a foreign key relationship mapping. So a SQL database looks like a good choice, but I will go with DynamoDB. The reason why I'm choosing DynamoDB, a NoSQL database, over a SQL database like Postgres is that we might, though we have not talked about fair discrepancy in the driver, in the functional requirements, on functional requirements. Let's say when there's a dispute between what the driver says and what the writer says about fair. But if we want to have that kind of situation, we need to ping the database continuously. Let's say after 5 seconds, every 5 seconds, once the write has started, from both the users, from both the drivers and the rider's devices, so that we can then add, in a scenario of fraud, discrepancy, conflict resolution, we can look into those locations at any point in time and figure out if the discrepancy, the dispute, how to handle the dispute. So if that is to be done in the future, Dynamo database is a better choice. So we have DynamoDB here, though with the given functional requirements, SQL database will just work as well. So we have a DynamoDB here, and your database will, your booking service will write to the primary database, and the user has now so this is get fair estimate. Yeah, the user, the rider now is looking at the screen where the system is telling him or her that, hey, we are looking for a ride. Now next comes driver client. This is also a mobile client, and the mobile client, before this, so the driver, so the rider now has looked into the fare, and they are happy with the fare and the ETA. So now they will send another request, which is patch/ride/book. And for this, we will have another service known as the matching service. So let me have another service here. And there are a couple of reasons why, There are a couple of reasons why we are going for a different kind of service, different kind of matching service, instead of we are using different service instead of booking service here. The first thing is that this particular work would be pretty complex. It would be computationally expensive, and we do not want to burden the system with this work. It will also help us to scale, to manage this service better. So that's why we are going to have a different service here, but we can obviously have a monolithic kind of structure. That's not an issue. So now API gateway sends a request to matching service, and matching service basically needs to figure out what drivers are in the vicinity of this rider. So there's another database which is your location DB, and the matching service, before that someone needs to update this location DB as well, and that would be the task of the driver client. So let's first of all complete that path, and then we'll come back to this one. So the driver client makes a post request to AWS API gateway with the endpoint / location, and for this again we need a different service, which is your location service. Update the location of the driver continuously. So this is update location. This is match. Yeah, and then we will have update from the location service to the location DB. Now we will come to this location DB in a while. Let's just keep it as a black box for right now. There's some kind of database which keeps track of the ladder launch of the driver. Now going back to Okay, now going back to this flow, we have a matching service. The location database gives us the details of all the drivers available in the vicinity of the given rider. But some of those riders could be busy, they might be off, they might be either available or they might be completing a different ride. So by the way, that could be another functional requirement where we are working upon a situation where a rider is about to complete a ride, a driver is about to complete a ride, and the request is near that drop-off location. So we should be able to have that situation as well here, that requirement as well here, but I will go forward and keep that as out of scope. Anyway, so we have the location of X drivers in the vicinity of a rider, and some of them are either available or and some of them are driving. They are in a ride. So the next task which our matching service needs to do is get the list of all those drivers which are available right now. So either it can talk directly to booking service or it can talk to primary database. Let's talk to primary database. Get available drivers. Now we have these available drivers, and just 1 second. Yeah, now this is not required, but anyway. Now what the system needs to do is send a notification or some kind of mechanism which tells the drivers that, hey, this particular rider is looking for a cab request, looking for a cab near you, would you want to accept it? And there are multiple ways to do that. One way is to use a WebSocket connection between the driver and the driver client and the AWS API gateway, and also between rider client and AWS API gateway. We will need it for other purposes. So that is one way where there is a constant persistent connection between the two machines, and your gateway can send a data to the client by itself. The other way is to use a notification service, which I'm going to use in this particular diagram. So we have notification service here, and we are going to use notification service, and there will be native frameworks which will be used, or I mean, whatever, we can use some other sophisticated framework as well, so that's not the issue here. So your matching service will send a request to your notification service, and with the details like destination and fare destination. Yeah, they should just like send it, and then the notification service will then send another request to this person, to the driver. Now the driver can make a request to AWS Gateway that hey, I want to accept this particular ride. So that is our fourth API call, which is batch slash ride slash accept, and this particular uh, you know request will go to the booking service, which will write accepted. And now what will happen is that it will update a couple of things. One, the status of the driver. So from available it will become booked, and then it will also update the driver who is assigned to this ride. So that's why, which was not available to begin with. So that's why if you remember, I suggested that there would be a partial ride object, and this is the reason why it was partial. So now the driver is booked. We have the location. We have given the location of the rider to the driver, and once the driver goes to the location of the rider, then the driver will make another request, which will be patch slash ride slash update, and both the calls where either he or she, the driver, has picked up the rider or has completed the ride, they will make another call here, which is ride update, and then the same flow will follow. Booking service will update the data in DynamoDB. Now there is one more thing. Once the driver accepts a ride, we need to update the client, the rider client as well, that your ride has been accepted, and this is the location of your driver, and this is how much time it will take, and other relevant details. Again, so this is where I was talking about that we could have used WebRTC for this kind of communication. We will have another a notification service connection from booking service to the notification service, and another connection from notification service to the rider, but I'm not drawing it here because it will just make it just too messy. So this ends up our high level diagram for the functional requirements. Let us see if we are completing all those, if we have satisfied all those requirements. So the first requirement was the rider should be able to enter the source and destination location and get the estimate fare. This is done. Rider should be able to book a ride based on a given fare. This is also done. And the third is driver should be able to accept a given ride. This is also done. Now there are a couple of problems with this design. This is not wicked fast. We have some non-functional requirements which talks about low latency. This search would be very slow in the given scheme of things, assuming this is a this is a SQL database. We have not talked about consistency. We have not talked about high availability and searches as well. So that is where we'll go now. That is the deep dive section, and let's hop into it. Okay, so the deep dive section. Let's look into the low latency first. Now there are a couple of problems here. So if I look at a location object, it will have primarily two things: lat and launch. The problem here is that we will need to the indexes which we set up on these two. Assuming we are using a SQL database, let's say a Postgres database. The indexes are structured using something known as B trees. These data structures are not structured to handle two-dimensional queries. We need to query two dimensions in a given time frame. That is, we need to figure out what the lat and launch in the given vicinity, and let's say draw a circle of around 1 kilometers or whatever. So for that, we can use something known as PostgreSGIS, which is an extension. So one second. PostgreSGIS. This is an extension which works on quad trees, and quad trees are data structures which are optimized to handle your two-dimensional two-dimensional queries. So we can use Postgres quad trees, PostgreSGIS, but again there are a couple of limitations there as well. And before I go into them, let me just do some back of the envelope calculations. Let's assume that there are 6 million Uber drivers, and out of them, let's say 3 million are available at any given point in time. Now this might be an overestimate, but let's just go with it. And let's say that they need to update their location every 5 seconds. So this translates to around 3 million by 5 equals to 600k writes per second. Now Postgres system is able to handle somewhere around 2k to 4k writes per second. We might increase that a bit by optimizing some writes, making some hardware optimizations and so on and so forth, but it will not scale to this number, which is 600k WPS. So that is one problem. This particular route, this load is very heavy, so our location database will not work. PostgreSGIS will not work. Postgres will not work. Postgres will not work. PostgreSGIS will not work for another reason. That reason is that so you see, we have around 600k WPS, and every 5 seconds a driver is updating their location. Now, as I mentioned earlier, PostgreSGIS uses quad trees under the hood, and they are good for querying, they are good for searching, but they are not good for reindexing. So every point in time, we are updating the location of a driver. We are asking the quad tree to reindex, and which is a very costly affair for data structure, for this kind of data structure. Quad trees are good in this situation because the density of different drivers in different areas vary, and that is where quad tree helps. Is that, let's say we have a lot of drivers in a location like Chandni Chowk, but we have very less drivers in, let's say, Sohna, then the quad tree will create branches which are more denser in your Chandni Chowk area, but less denser in your Sohna area. But so in that situation, quad trees or PostgreSGIS is a good alternative. But this problem, this frequent update, is the party spoiler here. PostgreSGIS might have been a good option in system design for, let's say, something like Zomato or Swiggy. Not Swiggy, only Swiggy, not Instamart. So for those kind of situations where we are not updating the location very often, PostgreSGIS might be a good solution, but not for Uber. So that leads us to the question, what next? The next solution is Redis, and Redis supports something known as geohashing out of the box. The difference between geohashing and quad trees is that geohashing basically implements something known as z-order curves so taking a step back, geohashing is a mechanism to codify the lat and launch into a at maximum 12 character string. So let's say I give the lat and launch of a particular place, they are then mapped to a string which is 12 character long. And the uniqueness, the great thing about this particular string is that it helps us query much faster. So as we are moving from 1 to 12, the degree of precision increases at each character. Now, if I remember correctly, if we have two strings which have 11 characters common, that is a precision of somewhere around I think a meter or so, or a centimeter, something like that. So the great thing here is that let's say 6 characters. Let's say 6 characters matching is equal to vicinity of around, let's say, 2 kilometers. We just need to do a lookup which says like and those 6 characters, and it will give us the list of the drivers which are in that vicinity. So that is geohashing. How does geohashing works? Geohashing under the hood works something on the basis of z-order curves. Uh, these are uh, mathematical curves to map a 2D or 3D data into a 1D data, which is what we are trying to do. Geohashing helps us to the great thing about geohashing is that now this particular flow becomes very easy. Redis after some optimizations can handle somewhere around 100k to 1 million writes per second, and this works great. Also, the retrieval is much faster because Redis is in memory. So we will be using Redis for this location. Okay, so now if whenever a request comes from the user, from the rider, from the API, from the matching service, that hey, we need to find the drivers near this particular rider's location in the vicinity of, let's say, 2 kilometers, the query would be super fast, and we can which this is a distributed database. So the first requirement is done. We will have those different low latency. Yeah, this is done. We will be able to query very much faster, and we will send a request to every driver, let's say, for 5 seconds. So in a 60-second time window, we can suggest 12 different drivers for this particular rider. So that was one check. By the way, if you really want to look into quadtrees and how does geohashing works, there are a couple of very amazing video tutorials which I looked into. I will add the description. I will add the link in the description. The second functional requirement, which was strong consistency. This is a bit tricky, and the reason why this is tricky is that this particular service will scale horizontally. So we will have an instance here. We'll have another instance here, and in order to so for consistency, just this now. So yeah, consistency now. So this block is for Let's talk about consistency. So there are two requirements which we need to consistency. There are two requirements which we need to satisfy for consistency. First of them is a write request should be given to only one driver at a time. Second is a driver should get only one write request at a time. And the first one is pretty easy. We can have one machine can wait for one instance can wait for, let's say, 5 seconds or 7 seconds, where we are waiting for the driver to accept or not accept the write. And if that particular write is accepted, then we'll update the status. If the write is not accepted, then we can move on to the next driver. So we have to make sure that the condition is a infinite for loop, infinite while loop. It's a while loop when the write is not booked. That's easy. The second part is difficult. That is, a driver should not get only one write request at a time. And the reason it is difficult is that, as I mentioned earlier, this particular service is horizontally scaled. So different machines will not know if a particular driver is given a request already by another machine. Um, and there are different ways to handle this. One is that we can add uh, a status in this particular uh, request, which is requested or something like that. And if the driver accepts, so now this particular logic here will have to look into the status of this driver. If the driver is in requested state, we do not touch him or her, and then we move on to the next one. The problem there is that we need to update the status again and again when the driver has not accepted the ride, and there's after the 5-second window has passed. We can have a cron job here, which does that for us. But again, the problem is that this runs at, let's say, I don't know, 10 seconds or 1 minute. Now that means that for 55 seconds that driver is in a booked state when the driver should not have been booked. When I say booked, I mean unavailable state. So this is not a good idea. A better approach is to use a distributed lock, which is again, let's say a Redis instance. And just 1 second. Let me just put it here. Yeah. Now this distributed lock has just a key value pair, which is rider. It's a true or false or whatever, doesn't matter. The more important thing is TTL, time to live, and this could be set to, let's say, 5 seconds. Now, whenever a matching service is booking, sending a request to a driver, at the same time they update this Redis lock with the rider ID with a TTL of 5 seconds. Now, if the driver accepts that request, then we have the happy flow here. That is great. If the driver does not accept the request, this particular entry vanishes after 5 seconds. The other thing this particular matching service has to do is that whenever it is querying the list of available drivers, it has to go one step beyond and see if a key is present in this distributed lock. If it is, then we move on to the next driver, because that driver is being served a request at that point in time. So in this way, we can ensure that only one machine sends a ride request to a rider at a given point in time, a driver at a given point in time. Now we could use the same Redis instance here, and that is great. Or the other thing we can do is we can have another driver lock table in Dynamo database, and we can decide TTL here, so that will work. Either of these two approaches could be done. So that takes care of the second approach as well, which is second non-functional requirement as well, which is strong consistency. Now high availability is kind of a general answer. We should be able to have scaling and situations like that. The fourth non-functional requirement is interesting, and the way to handle this is have a queue in this situation. So we have a queue which this is fine. Now this particular queue takes care of all the incoming requests during a search and allows the system to scale at its own pace. We cannot just scale the system in a very less amount of time if the number of request just jumps exponentially in a very small time frame. So this queue acts as a buffer for a booking service. It makes sure that the system doesn't collapse. However, we need to make sure that the queue is either sharded according to the location, because let's say in the previous example, when a lot of riders are coming out of Ahmedabad Stadium, we do not want rider in Gandhinagar who is trying to go to Ahmedabad right now, and there are a bunch of drivers available, but the rider is not getting a ride. His or her request is not being processed just because there are X number of requests stuck in the queue because the system is not scaling. So we need to have a system where this queue is sharded according to to the location, and this would be a FIFO queue. So that will be it. And then there are other types of optimizations, like the system will not be a single instance. We'll have a couple of instances in, let's say, Northeast US, Northwest US. We'll have another a replica of the system in Mumbai or Singapore or in Dubai or yeah. So that sums up the video, the design. For this particular video, I took a lot of help from a couple of design videos. So first of them is here, and I will link them in the description as well. But yeah, so the first one was from Hello Interview, and then I have the others are, anyway, I'll list them in the description below, and that's it. That sums up our system design for Uber. Cool. Chalo, thanks. Bye.